So I'll be talking about automated NDE in factories and focusing on modular and interconnected systems. Because as soon as we talk about automation, we cannot have standalone systems or subsystems. And when I say systems in our case, we're talking about inspection systems, we're talking about instrumentation, we're talking about reporting. So we cannot have standalone reporting and instruments that do not integrate with the factory environment, because there's no way we can automate it with that. And there's going to be basically three sections or three big areas that I'm going to talk about. The very first one is the difference between mechanization and automation, then a few case studies, and then finally a mechanism on how we can achieve factory automation. So that's me talking, but it's all Dave's work. So if you have good things to say, I'll take the credit. And if you have other feedback, I'll pass it on to Dave. Okay, so NDE in the modern manufacturing context and what it means, the fact that mechanization alone is not enough. And when I say mechanization, we're talking about making a gantry go back and forth and collect a C-scan, or a robot basically move the probe or the part and collect data. That is still mechanization. I think automation is a much larger ecosystem that we're living in. And then finally, we're going to talk about what the customers are looking for, or the modern customers are looking for, and that is data fluidity. Data should be able to move from one domain to the other domain. As we go on into more, whether it's rules-based or machine learning-based algorithms, you cannot have the data stuck in a particular software or in a particular format. You want it to be portable, essentially. And the big one is equipment interoperability, because there are really great instruments out there. A lot of them, TPAC makes them as well. But if we get stuck in a factory with one instrument, and just because the automation and because the file format and everything else should not be preventing you from using the latest and the greatest or state-of-the-art technology. So the whole idea on that is we want to make everything interoperable. So just as a comparison between the legacy approach of NDE and the modern approach of NDE, NDE used to happen, I think it still happens in a lot of places at the product level after the manufacturing process. It is slow, and slow can be because of data collection speed limitations, analysis limitations, or reporting limitations. And also the data becomes inaccessible because it's in the form of paper records or PDFs. Now, they're really great for archiving. They're really great for going and looking something up when you want to go and find more information about that data. But it does not really help if you want to do a meta-analysis on that. I'll touch a little bit upon what I mean with that. Now, in the modern sense, let's take big forgings, for example, including the one that it was bearing raceway that Gavin had showed earlier. NDT happens at multiple stages. It will happen at the billet stage. It will happen once you have cut it up into pieces before final machining, and then it will happen after final machining. And the whole idea is you want to do NDT, or rather you do not want to process the material any further if there is a big crack or big flaw right in the middle of it. I think at that point, you just remelt it and start all over again. So it is an expensive process, and that's why you want the NDT to be happening at every stage of this manufacturing process. It needs to be fast, so it needs a lot of times, especially when we make, and fast happens in both cases. If it's big parts like airplane wings, we're talking about acreage is the word that has been used at times, because you're analyzing acres of data. And an analyst has to go through that. So we do want to make it fast for those. And then it also needs to be fast for what runs in the bearing raceways, like each of the bearings, because there's a lot of those bearings. So you cannot really afford to sit and do the entire process manually. At least the first round of it should be fairly automated. Okay, so mechanize versus automate and automation. So this is a really, really interesting insight that we found. And it's all thanks to Google, because I think around 2000, Google started digitizing a lot of books. And then a lot of the new books that are there, or information or publications, that's already digitized and Google has access to it. So, a lot of us here deal with data, and Google deals with a lot of data. And they said, hey, why don't we give people a histogram of the frequency with which words appear in written documentation, all the way from wherever Google decided to digitize those. That's automation. Sorry, that is mechanization, and this graph shows the frequency with which the word mechanization has been used since the 1920s. And you look at it here in 1960, it seems like it peaked up and people said, we're done. We don't want any more mechanization, which we all know is not really the case. So look at automation. We'll not go on the dictionary meanings. They sometimes talk in circles. It doesn't really make much sense. But when you look at automation and you search for automation on the Google Ngram viewer, you get that. And that is very interesting. So not just the fact that there's a peak that kind of corresponds with mechanization in 1960s, but then there is a second hump here and a third hump which is happening here. And we're like, okay, what's going on? So we did a little bit of research, and this is what we think happened. PLCs started gaining a lot of popularity in 1960s, and that's why there's a big hump there. And after that, it was taken for granted. I mean, PLCs are PLCs. Mechanization is just there. You're not going to start writing papers about it. Any guesses for what's happening here in 1990s? Computers, perfect, yes. And that's what happened. Like, personal computing kind of became really, really popular out here in the 1990s. Windows came out, and then the world became a very, very different place. And we all know what this one is. I don't have to explain that one. And it's not. It does look like a plateau, but it's really not a plateau. I think it's still a curve that's going up. So you can go on Google Ngram Viewer and have fun with this. If you just change the words, if you use mechanize and automate, it's a very different graph. From the statistics perspective, if you're looking at trends, it is still conveying a similar information, but this was more to scale, so I used this one instead. Okay, so let's go on in. I'll talk a little bit about NDE automation from where it started, because these days a lot of us talk about NDE 4.0, but let's start from the very beginning, from NDE 1.0. So anything in orange is manual, and then usually a new idea comes along, and then that idea gets automated, and then eventually you go towards NDE 4.0 or Industry 4.0. So, and new ideas are, PCI, plane wave imaging, and phase coherence imaging. All those are new ideas, and at some point of time they will just become adopted and become a part of the fabric of NDT. So the next stage was, hey, why don't we start scanning stuff and then do some analysis? And this was a lot of handheld instrumentation and early flaw detectors. And then the next phase was, why can't we just automate? It says automate here scanning, but that's talking more about mechanization, where the probe is moved in a raster pattern or in a circle to generate a C-scan. And it's very interesting, from the early 1970s, some of the C-scans that these tanks were producing, the format was thermal printing. There would be either a plotter or a thermal printer, literally printing out your C-scan that's going out there. But that's where we're coming from. I think that is more, I guess, 1970s and 80s at that point. And then we start putting it on paper. So there's strip charts, C-scan plots, etc. And that was all NDE 2.0. The next generation of it started when the digital stage came in. That's the 1990s, when we could actually get the C-scans or images or data on a screen, and we could put it there and keep it there, and then a fair bit of automation happened at that end. The next step was where calibration, alignment, like we were starting to grow our field here. We started out just with sensing, and now we're talking about everything to do with the sensing before and after, which is the calibration, alignment, and then on the other end we're talking about reporting. And eventually we're talking about assisted defect recognition, whether it is rules-based, machine learning-based, it doesn't really matter, whichever one is adopted by the industry. And finally, I guess this is where we are not there fully yet, where the analysis itself is a completely automated process, like everything down here is green from one end to the other end. And that takes us to Industry 4.0 or NDE 4.0. Now, where are we in this? This slide, I think the first version of it we made in, I think, 2009. And since then, we have progressed quite a bit as an industry. And right now, we are there. We are still not quite all the way to, everything is completely automated. But I remember seeing the same presentation, probably making it as well, where we are somewhere further up in the last 16 years on this list. So this is just a sense of where we are when it comes to NDE automation and where we can go. So the next few slides are a few case studies, some on data analysis, some on data collection, to give us a sense of how we're getting there. So in this particular case, a lot of samples are inspected at the same time, and then the software automatically crops them up into pieces and does the analysis on those pieces and does the reporting on those pieces in a global database. And the entire process is completely automated. So the job of the operator at that point is to load the parts, and then that's it. The system takes over from that point on. The second one is again related to bearings, and in this case we're doing the bearings themselves. And this is conventional UT, high frequency. The entire system is controlled with a PLC, and because there are so many bearings, there is no way but to do cycle times less than 60 seconds for it to get through. Now, the first stage of analysis is already done before the system moves on to the next bearing. And this is a result or a screen of the first layer of analysis that happens, and this is all rules-based analysis. We have done all the setup, and bearings do have the back wall, which is not straight. So all that has been taken care of up front. The bearing goes through the process, and it is rejected if things are found inside the bearing. And at that point of time, an arm comes in and pushes the bearing in the other rack. Now the data is still there. Whenever it fails, we save all the A scans, all the waveforms, everything into a data file that can then be looked at for more in-depth analysis on where the problem is really coming from. That's the next generation of the system, where it is a UT and eddy current machine combined. So there is a head in this machine that does the UT. The bearing moves on to the eddy current region, and it gets the eddy current done on it. And this entire system is completely automated, and even the data is stored in the same data file. So there is one data file for the bearing, and it has the UT data and the eddy current data. Because if we are really talking about, I talked about data fluidity and information fluidity. So the first step where we start doing it is why separate them to begin with? Why can't we just keep them in one place? So that was this particular system, and the results obviously are reported in real time for that. So keep a track on time. I'll take 3 more minutes. I'm going to talk about something other than bearings, and I'm going to talk about fully automated systems. And in this case, it's a automated cell for doing aircraft clips. There are over 2,000 part types, and you can add more without coming back to either the machine builder or the software provider. The customer themselves can add more parts to it. It is multi-inspection. It's not very clear here. You'll see it in the video, but there is the radius probe there and a flat probe in here. And you can do a lot of those. You can add more probes to it if you need it. And then that's the big one. It's multi-instrument. I really love this instrument, but let's say you have come up with a new technique which this instrument doesn't support. You can take this instrument and replace it with an instrument from a different vendor altogether, and nothing changes on the automation end. I mean, you still have to requalify the machine or the system, but you don't have to go back to the machine builder or the software developer. Everything is there, fully under your control. You can bring on a completely new system. So let's just take this thing and see it in action. I don't think there's sound here, so you don't hear the beautiful music. That's bad. He's reading the QR codes of the nests and the parts that have been put on it. It flips around so that the operator can keep loading new parts. And on the other side, the robot picks up one of the appropriate tools. There's 3 in this cell. It picks up this part, and it's going to do 100% inspection on that. So all the flat faces and the radii are going to be inspected. So that's a regripping station. It picks it up there, and it goes in and starts collecting data. Now, in this meantime, the part has been adjusted for, grippers are not perfect, so you do have angles and so on and so forth. So all that has already happened. Like the robot has gone and fixed, that's automation. The robot has gone and fixed its nominal path that was taught to it. When it picked up the part, it realized it was slightly at an angle, and it has already fixed it while you were watching that video. So this one is 30 parts an hour. All these different faces are different scan files. But as soon as the inspection of a clip is done, we merge all that together in a single data file. And when the analyst starts looking at it, it's one file. And to make things even faster, the same QR code that this part has, the analyst is going to scan the QR code, and the data file is automatically loaded and ready to go. OK, so how did this all come around? It's basically the second part of the presentation, which is modularization. We want to break a bigger process into smaller chunks, not too small, but not too big either. So in this case, that's the data collection engine. That's the automation engine, and they talk to each other. And in our past lives, Dave and I have done systems where these, along with analysis, were the single application, and there was no way we could scale that up. So on the data collection engine side of things, it is interoperable because you can replace instruments. That's the reason why that robot cell can get a TPAC instrument overnight, because it was designed to be interoperable. And on the analysis end, it's the same idea. IW Automate is talking to the analysis software, and it takes care of communicating between them. Like you say, calibration is valid. That information from here is sent to the Automate software. It keeps a track of it in the database. And it also will start putting in the information about what the calibration part was, who analyzed it, et cetera, as a metadata of all the inspected parts. And it can also put the data in there as well. On the other side, that's the machine side. This is basically just a robot head. We reach a little bit into the machine space. If you see a lot of the machine builders here, and some of them we work with, what we do is, it's a state machine. We reach a little bit into the machine space. They reach a little bit into our space. Whether it is using OPC UA or sockets communication, it doesn't really matter. The protocol is well established. We can flip from one to the other. And you can replace a robot with any of these machines. Nothing changes on the right-hand side. On the right-hand side, your UT or your NDT is completely independent of how the automation is done for collecting the data. And then why stop there? Why do we just not keep going and we replace this side with any kind of NDE technique? And then, in principle, the same piece of software can open and analyze any of those data. Now, it's more evolved on the UT and Eddy Current at this stage, but the other types of data files can be loaded and looked into. And then the whole thing hinges on modularity, and modularity is where we start. not where we end. If we start at modularity, the right side of this slide can completely disappear and be replaced by the data collection software of the appropriate technique or of the appropriate application. And to bring this along, there's a few things that we have to look at. The very first one is inter-organization collaboration. We have to talk amongst machine builders, amongst instrument manufacturers, so that the data file, the machine controls, they can move from one to the other. And without this collaboration, it is not going to work out. We'll be still stuck into single-purpose machines. The second part of it is a suite of enabling technologies, and they keep coming along, and we keep putting them in. The third one is the connectivity between machines and the larger systems. So we want to make it possible that the factory database is able to interact with the machine interface, which can then interact with the NDE interface. So we don't design it upfront to be monolithic, like everything goes into one. It's in exchange of information. And then finally, the connectivity of the manufacturing information system with each other. So NDE results on let's say, an aircraft wing. The production guys aren't interested in a 1-inch defect, 5 inches from the left corner or something like that. They want the location in aircraft coordinates or spacecraft coordinates. I mean, that's the only thing that works for them. Or if you're doing corrosion inspection, they want to know exactly which course and which plate is the one that they have to go and fix. So whether you're collecting data with a robot or manually collecting it or collecting it with crawlers or drones, at the end of the data, if the information fluidity is there, the NDT software will be able to bridge the gap from isolated systems to fully connected and interoperable systems. So that's it. Thank you very much. I'll be happy to answer any questions.